My name is Patrick Burns. I'm the CEO at Croom Medical. Today we're going to discuss our efforts in collaboration with Global Advanced Metals on 3D printed tantalum and next generation of orthopedic implants. So here we'll be hearing from myself on an initial introduction to Croom Medical, our story with the development of laser powder bed fusion systems within orthopedics, and why we've selected tantalum, leading on to our long-term relationship with Global Advanced Metals. Then you'll hear from Dr. Gordon Smith, CTO of Global Advanced Metals. And then finally, we will relate to Dr. Shane Keaveney, Research Development and Innovation Manager at Croom Medical. Croom Medical is an orthopedic contract manufacturer based in the south of Ireland, based in Limerick in the south of Ireland. We're nearly 39 years in business. Next year will be our 40th year. We are a second generation family owned company, and we operate a 24/7 production facility of nearly 170 staff members. We are a contract manufacturing house for much of the household blue chip names that you'd be aware of within the orthopedic space. We've invested very considerably within our plant and machinery over the past number of years, with further investment in the horizon in 2024. We will soon be launching an additional 24,000 square foot facility, due to begin in Q1 of the next calendar year. We are FDA registered. We have ISO 13485 accreditation and 14001. Much of our growth to this point has been underpinned by our research, development and innovation team that have orientated around the development of laser powder bed fusion systems, which we have been supporting with our blue chip customers for the past decade or so. You'll see on the video within this slide deck that it's supporting a number of advanced technologies such as the integration of automation. So it's not only the 3D printing aspect of orthopedics, but it's also the ability to respond to shockwaves within the supply chain to take costs out. So with that said, our efforts within laser powder bed fusion systems have orientated around the material development in an effort to add more value within the supply chain and offer a diverse, broad span worth of process development approaches that we can offer to our blue chip customers, both nationally and internationally. So our efforts within the orthopedic space, so why are we looking at laser powder bed fusion systems more specifically? So we have noticed, much like most of our other competitors and customers within the space, that there is a fairly aggressive growth within this region, right? So we're seeing nearly, if not some aspects, over 30% growth, compound annual growth rate from 2021 to 2025. So we've seen rapid adoption over the past number of years within laser powder bed fusion systems to be adopted within the orthopedic space. Predominantly, this growth is being driven by hips, acetabular cups, and closely followed by knees and then spine. To give you an idea of the amount of adoption, or the rate of adoption rather, nearly 10% of the FDA 510K submissions, which were submitted in the first 6 months of 2022, all had additive manufacturing within their portfolios. And out of this portfolio, then we're talking nearly 70% for spine applications specifically. So within these applications, we're seeing a big emphasis within the osteoconductive structures that can be supported within spine lumbar cages, acetabular cups and surface, and also tibial base plates. So why are we looking at this process map rather? What's the big hoo-ha? So from our perspective, it's customized patient-specific implants, what the market is willing to pay, but also the optimized topology and graded structures. So we're seeing a process technology that's had the ability to quickly iterate prototypes and also quickly iterate patient-specific implants that would typically not be possible in the past. And that's something for us that's been a major upsell in relation to impacting international markets. Our research and development team has been very strong within the material development and also the process development itself, post-processing, such as the cleaning of osteoconductive structures. What we're seeing in the horizon over the next decade or so would be the multi-material integration that's feeding under these market dynamics as well. So from our perspective, our intent is to develop materials and processes that can address the market in the next decade and beyond. And finally, we are seeing some innovative implant technologies orientating around graded structures, but also the adoption of orthobiologics, which is something that's not too distant from us based on the progressions that we've seen with our academic partners, but also with our industrial partners, such as Global Advanced Metals. So why tantalum? So in OMTech in Chicago, in June just gone, Croom Medical and Global Advanced Metals launched their initial prototype of a tantalum and titanium tibial baseplate. So the image on the right-hand side of the slide here shows a tantalum osteoconductive structure and also a tantalum keel that's bonded to a titanium substrate. So for us, typically you have blue chip companies that have used tantalum quite well, adopted widely in the past. But the innovation for us within our orthopedic materials, essentially we identified a market demand that could be adapted to a new process technology within the orthopedic joint replacements market. We've seen titanium, specifically commercially pure titanium and TI64 being adopted to the initial implants that had been launched over 10 years back. First starting in the hip cups by Lima Corporate in Italy, and then following on from that, you would have had the titanium base plates done as well for the knee systems. So we are seeing some long-term evaluations and challenges where we are seeing some aseptic loosening of some of the tibial base plates only recently in some web science papers that have been recently launched. And we're seeing a number of surgeons that have directly contacted us in relation to some of this aseptic loosening and how we can basically design an implant or material type that would combat this matter. Building on from that, we're seeing tantalum has a history of enhancing stability and longevity within the orthopedic space. So our internal research and development and innovation team has identified that compared to titanium, tantalum offers both a superior coefficient of friction against cancellous bone. It enhances both the stability and the longevity of the implant, and we're seeing that across the board. It's not just the tibia base plate trays either. So tantalum has some remarkable attributes. Consistently demonstrates remarkable attributes in research such as biocompatibility and corrosion resistance. So from our perspective, we went to market once we realized that there was an opening here for material development within the tantalum space. We quickly came to the conclusion that not only was it very difficult to get a solution provider of a laser powder bed fusion system that could provide us with an asset to essentially develop this material further, but acquiring the material itself was quite a challenge. And that brought us to the collaboration with Global Advanced Metals. So Croom Medical, we are a high volume medical device contract manufacturing company, predominantly in the implant space, not instruments. We are experts in additive manufacturing for medical devices. So as I mentioned, this has been going on here over 10 years now. We have 9 postdoctoral research covering a number of areas of research, such as kinematics of machines, but also material science as well. We are ISO 13485 accredited, and we have been actively involved in national and international research consortiums, particularly across the EU. Global Advanced Metals is a global leader in tantalum material production, and speciality is non-conflict high purity powders designed for additive manufacturing. It has exclusive mineral rights to the mines in Australia, and it has decades of high purity powder for capacitors and semiconductor industries. So with that said, I'm going to hand you over now to Dr. Gordon Smith, Chief Technology Officer at Global Advanced Metals. I'd like to thank you for your time and looking forward to reaching back in relation to the questions that you may have at the end of this presentation. Thank you.
Thanks, Patrick. Again, welcome everyone to joining us today. Glad everyone could join us. I'm going to expand a little bit on what Patrick just talked about when it comes to tantalum and its use in medical devices. I'll touch on a little bit on some of the interesting properties of tantalum. I think it's also important for us to all kind of get at least a general understanding of what's happening in the market from a tantalum demand and supply standpoint, so you can understand the size of the market and where it's currently used. And I think it's going to wrap up then with a few comments on the stability of our AM powders, and then we'll hand it over to Shane, and he'll talk about the print platform. If you look into the medical industry, you might be surprised at the number of commercial applications that currently depend on tantalum to offer a unique feature within the medical device. For example, Zimmer Biomet, they have their proprietary trabecular metal technology, which is used to produce a range of devices, such as hip and knee implants. This leverages tantalum's osseointegration performance. In 2022, Zimmer Biomet completed the spin out of ZimV, who now carries the full line of dental and spinal implants, also based on the trabecular metal technology. Bone integration here being a big driver for using tantalum in these applications. You'll find medical staples and clips on the market, such as ligation clips from Teleflex, which leverage tantalum for its mechanical and radio opacity characteristics. And beyond that, there are quite a number of products which actually add tantalum as a marker for procedures such as fluoroscopy. You can find stents produced by Boston Scientific, which have small tantalum markers on the stent, as well as liquid embolic systems from Medtronic, where tantalum particles are added to the liquid to make it radio opaque. So it might not be initially apparent, but tantalum has been widely accepted and used then in the medical industry for over 25 years. So on the previous slide, I hinted at some of the attractive properties for tantalum in medical applications. One of the drivers is superior biointegration. There is an ample amount of literature that tantalum offers enhanced osteoinduction, osteoconduction, as well as osseointegration when compared against most other implant metals. Induction, of course, being cellular activity preceding bone growth. Conduction being the process by which the growth of bone happens on the surface, and in integration being the interconnectivity of the bone within the device. Now, there are a number of growing applications that are implementing tantalum due to its radio opaque properties. Very important for real-time monitoring during device placement within a patient. Comparing to other common metals that are used here, such as gold and platinum, tantalum offers a more cost-effective solution in these applications. Looking at some of the mechanical properties of tantalum, tantalum offers, a very high ductility, which lowers the risk of brittle fracture, with wrought tantalum demonstrating in excess of 35% elongation at break. Now, we have found it very interesting that when printing with our tantalum powders, off the printer, we are seeing 40% elongation in the build direction. So a little bit better than what you would expect from wrought tantalum. Now we can expand further on what makes tantalum an ideal material for implanted medical devices that interface with bone. If you're looking into the literature, tantalum is an ideal material for implantable medical devices due to demonstrated biocompatibility with resistance to blood clot formation, enhanced bone ingrowth, low modulus, high normalized fatigue strength, and high surface friction. With respect to blood clots, thrombus formation post-device implantation is a real risk and can lead to strokes, heart attacks, and even death in some cases. Indications in the literature, you'll find tantalum helps prevent this side effect due to resistance of blood clot formation. In addition, unlike many of the alloys that might be used for medical implants, where it has been noted the potential to release toxic or mutagenic ions, tantalum is 100% biocompatible. Now, I've mentioned already a number of times about enhanced bone ingrowth, osseointegration. I think it's a huge benefit with tantalum devices. When compared in controlled studies, you'll find in these studies against common materials like Ti-6-4, tantalum exhibits statistically improved bone grafting performance. So in addition to the ductility that I mentioned on the previous slide, tantalum's modulus is a good fit for preventing stress shielding issues in bones. Again, if the mechanical properties of a medical device material do not match closely to that of bone, then the bone is shielded from the stress leading to bone loss. Tantalum has a high normalized fatigue strength. Tantalum should not catastrophically fail if it were to be deformed over a significant number of cycles, which is a nice benefit. And lastly, high frictional forces are important when inserting or placing a medical implant within bone. Friction will hold the medical device in place as the bone grows into the device. Tantalum exhibits, high surface friction, offering device stabilization, after implantation. So tantalum is a great material for medical devices due to its technical characteristics, but the amount of tantalum used in the medical industry is far outstripped by other applications. It is highly likely that everyone here on the webinar today is currently being supported by tantalum. Most of tantalum's uses today and in the future will be driven by the electronics industry. Tantalum has been a key material used in capacitors for over 70 years. This is primarily due to tantalum's characteristic of having a very high volumetric capacitance efficiency. It's also interesting to find, if you look at semiconductors, greater than 95% of all semiconductors produced today use tantalum in the stack structure within the circuitry. Tantalum forms a critical barrier layer between the copper circuits and the underlying dielectric layers. So another interesting application is actually in aerospace. Here to leverage a little bit different property, tantalum has extremely high melting point, 3000 degrees C. So it offers alloys that can perform at elevated temperatures. This permits then the engine designers to operate engines at higher temperatures, which then increases fuel efficiency for the engine. Now, so the way we look at this is that the medical industry can continue to leverage, this developed capability and the very high purity tantalum that's produced in these other demand leading applications. So if you look at a little bit of the history of tantalum supply, 15 years ago, most of the tantalum came from hard rock mining in Western Australia. This was purposeful mining of tantalum or tantalum ore. Now, hard rock mining, proved a stable source, but relatively expensive. Roughly in about the 2010 timeframe, due to the implementation of robust traceability mechanisms of material coming from Central African sources, this open trade to global markets. Something called artisanal mining then came along of tantalum, particularly in the DRC and Rwanda, and then this replaced hard rock sources. This material from Central Africa, though, was considered less expensive, but does contain inherent instabilities, both political and by the nature of the unstructured mining methods that are used. Now, it's interesting that the high demand now for growth for lithium is attracting major investment in lithium mining expansion. We all know about EVs and the EV explosion, lithium needed for batteries. So many lithium ore bodies, it turns out, are also rich in tantalum. And so we are seeing a fast approaching structural shift in the supply tantalum derived as a co-product of the lithium mining process. This source is growing now and should reach 40% of the world's supply in the next 2 to 3 years. Now, the majority of this material, again, is coming from Western Australia, where GAM, Global Advanced Metals, we own the tantalum rights in multiple lithium mines. So the way this works is as lithium producers mine and process lithium ore, we take that ore and we extract the tantalum out of the ore and give the ore back to the lithium producer. So this offers a very ecologically friendly and alternative source to the production of tantalum ore. So as the global demand for EVs and lithium continues to increase at 4 to 5 times by 2030, tantalum production will come along as a co-product, meeting the market demand. So Global Advanced Metals, and we offer decades of experience producing ultra-high purity tantalum products. We are fully integrated. Again, we bring ore from the sources in Australia to our facility in Pennsylvania, US, as well as a facility that we have in Japan. We use various chemical processing to extract the tantalum and produce then very high purity tantalum feed. We have a sterilization process that then produces powders for additive manufacturing. We've spent the last decade developing a full range of powders for AM technologies, such as direct energy deposition and laser powder bed fusion, with the primary target market being medical applications. So briefly, just to look at the type of products that we produce. GAM, we supply various spherical powders again, primarily for AM, additive manufacturing. These products are very high purity and have very little oxygen content. We do offer angular powders, which also have very high purity and low oxygen. These are primarily targeted at other coating technologies such as cold spray. I have previously mentioned electronics and capacitor powders. This is a major driver of our business again, and even gets us into nanotechnologies. We have nano powders that enable ultra high capacitance capacitors. And lastly, we do have bulk type products, wrought products, covers plates, bars, and billets. Main products here are sputtering targets that again go into semiconductor manufacturing. Because before turning it over to Shane then, I'll just wrap up a few comments on powder stability and safety. We continue to look at the stability of our powders, one being shelf stability. Very fortunately, we are observing very stable shelf performance. Where powder stored in ambient conditions, we see very little oxygen uptake. And the data to date is over half a year, so very stable powders. Now, overall safety is very important at GAM. So we have completed a range of ignition testing on the powders that we produce. We find the spheroidized powders for AM manufacturing, additive manufacturing are extremely safe. In some tests, even indicate table sugar has similar hazardous performance as our powders. So with that, I'd like to then turn it over to Shane, and he'll dive into the print platform that's been developed.
So, hi everyone, I'm Dr. Shane Keaveney. I'm the R&D manager here at Croom Medical. I've been working on additive manufacturing research academically and in industry for about the last 10 years, and the last 6 of those have been with Croom. So focused on their metal SLM systems. So well, I'll just take control here. So just in terms of, I suppose, from a research point of view, what our goals are. We've heard a lot from Patrick there about the trends and Gardner and tantalum. So for us, I mean, our goal is to advance manufacturing technologies to enable better patient outcomes. So as a subcontract manufacturer, what we want to do is have better technologies, better manufacturing capabilities on the design, the hardware, the software, everything, so that our customers can leverage us then to achieve better results and hence achieve better patient outcomes. So that's where the motivation around additive manufacturing and tantalum has really come from. So in terms of our additive lab, we have a number of different systems from Renishaw, Concept Laser, and also our GE M2 to print with various different materials. Quite a focus on titanium 6.4, obviously, for medical implants, which we use for the production of medical implants, which are FDA validated and approved. And we also have then our M2 Series 5 machine, which is 100% dedicated to tantalum. And we've optimized this machine for actually working with tantalum due to the unique properties of it, and also obviously developed out our print process and print parameters and our general operations with that machine for the particular material. Now, as well as building our capability for additive manufacturing through our machines and through investigation in the machines, the parameters, process monitoring, we also have our materials testing lab as well. So within there, we can do morphological, mechanical, various analysis of our printed materials and powders as well. So for instance, mechanical testing, mounting and polishing to look at the microstructure evolution, investigate our heat treatment, density, and also analyze our powder characteristics as well in terms of how they're changing over time, which I think is a very key piece to, especially for additive manufacturing through SLM, where we're working with the powder. So the powder obviously is one of the variables in there, and it needs to be monitored, but also the results of the printing need to be monitored very carefully. So that whole side of quality control through our material testing lab has been quite key, and obviously key to the development here with tantalum. So I guess we've heard a lot, as I said, Patrick kind of talked about the trends there, and Gordon about tantalum. We've heard about the benefits. So for us, I mean, there was a real keen interest here in the additive manufacturing of tantalum due to the trends within the medical device industry and the benefits tantalum can offer. And from what we have seen out there, tantalum is manufacturable in numerous ways, but to achieve the type of structures we want, particularly for the porous osteoconductive structures, there's limited technologies. So that's where the additive manufacturing through SLM seemed like an interesting topic. SLM in particular, due to the feature sizes that we can achieve, and with the porous structures that we're trying to achieve, we're looking at very small feature size of maybe 200 microns. So, and now in terms of additive manufactured tantalum, there's, as you've seen, there's a good bit out there in the literature, over the last couple of years, and it's increasing. So there's a trend there of more investigation into it. So for us as an actual subcontract manufacturer rather than an academic research institute, we were keen to see, could we replicate the results seen in the literature at a scaled up industrial level to then offer to our customers. So we've seen that porous tantalum nearly matches the modulus of bone and has highly effective osseointegration. Obviously, in terms of patient outcomes, this is very key. So we have the aseptic loosening and the time of recovery and integration with the patient. So critical point. This point around high ductility and large plastic deformation kind of lends into what Gordon was saying about fatigue properties. So it's a very, very tough material. It has a large plastic zone and it's a very tough material. So that's very, very beneficial if we have, say, larger implants or implants that are under cyclical loading or that may have some potential for strain to happen. There's less likelihood of a catastrophic failure. So like Gordon mentioned towards fatigue. So that's quite an interesting property, and I'll go through a little bit demonstrating that result in a bit. As I said, there's quite a significant amount of published research. So that's proved the feasibility, and it also has shown the improved performance from using tantalum. So as for us, we wanted to demonstrate that in a scaled up fashion in industrial settings. So the other 2 points here, which are quite important for our collaboration with GAM, is that this is a very stable process, the printing of tantalum, and I'll show results around the powder stability during the process, but the powder supply chain is also quite critical to the entire system. So again, for additive manufacturing, where we have a powder source, the powder supply is quite important. And if we look at the last couple of years where there's been major supply chain issues, and especially if we look at titanium, there's quite a demand on that, and there's been issues there in the supply chain. The supply chain for tantalum is quite important. So with our collaboration here with GAM, we're able to close that powder supply chain, which not only gives us a stable source for the powder into the process, but for the recycling of the powder after printing, it's quite key. So instead of us having to, say, throw away powder or lose powder when we're done with the number of cycles, we can run it. GAM is able to reprocess that within their own processes. So again, that makes a more closed supply chain there for the powder. So quite important. And it's one that has been highlighted in the literature as well. Now, just what I want to go through is a little bit on the results we've achieved at a reasonably high level, just so you can see where we're at, what we've done, and that how we've demonstrated we have a nice printing process. So obviously the first thing I want to look at was the mechanical consistency and also the solid material performance. So to do this, we have a relatively simple build here. So we've looked at, I'll just get my laser pointer. So we have a number of different, basically we have 5 kind of different sections here with the 4 quadrants in the corner and a central piece. Now within this, we've done compression testing, density testing, and tensile testing. And you'll see the layout here from above, and we have our printed samples here. See, from visually looks quite consistent. But if we look also on the melt pool monitoring, which we have on the M2 system, which does melt pool emission monitoring as well as melt pool size, we can see we've obviously quite consistent color map here. So looks quite good. Now we're using this melt pool to help us in the development of the process as well. It's been quite useful and good for overall quality control as well when we're working with, say, new geometries or what you might have. We just scroll on to the next page. Just in terms of the actual results then, I've just taken out a sample here for, this is on the tensile performance mainly, but we've seen similar results across the compression and density as well, similar consistency. So if we look on the left-hand side, I have the plotted aspects, so UTS in blue, proof stress in orange, and Young's modulus are, yes, here in gray. And I've plotted this basically across the build plate in the X direction on the left and in the Y direction on the right. So moving from -100 millimeters on the X up to 100 millimeters on the X, you'll see we have minimal change across here. And similarly on Y, again, minimal change. So quite a stable and consistent process on our plot here. Moreover, if I look at the standard deviations for both proof stress, UTS, elongation, and the reduction area, again, you see these are quite low. So quite consistent for elongation as well, which is very good because elongation is one that's a little bit more sensitive due to the nature of how a failure happens during tensile test. It takes a very minute kind of defect on the sample that might change the elongation between 2 samples. So quite good to see. So that's in terms of our solid. We've developed out those parameters over a number of DOEs. We've investigated compression, tensile, and density as well, seeing good consistency. So we're very happy there. And the overall results we see in terms of mechanical performance are quite good. Now, in terms of the porous, which is the other side of we're looking at an implant, and we've done some work here in terms of, again, a number of DOEs to understand the process, the behavior of the printing, and the behavior of the printed structures as well. So as we've seen in a lot of the literature, we've just used like a typical diamond cell here to get some nice results, 1.5 mil cell size, and we targeted a 200 micron strut diameter. And with this, again, I've gone for a regular lattice opposed to stochastic just for this type of compression testing, as it really more consistent results give us better information here. In terms of the results we've seen, highly consistent. We're able to go from strut diameters of maybe 200 microns or a little bit less up to 400 microns, and of course beyond there as well. So very consistent. Easy for powder cleaning on these structures too, which is one of the points I guess we haven't touched on much here, is the density of the tantalum. So it's around 16 grams per, I forget the exact units there, but it's about 4 times that of titanium 6-4. Now, that on one side makes our parts heavier, which is one piece, but we'd aim this printing process more towards lightweighted porous structures. However, for the powder, it actually helps a great deal with the flowability of the powder and also the cleaning of the parts too. So with the heavier powder, obviously it's easier for gravity to work on it and clean these structures out. So we found cleaning to be good as well, and the flowability for coating as well, quite good for the powder. As I said, quite consistent results in terms of the overall geometry, quite a range of geometries, good control. The other piece then, I'll just see if this video will play. In terms of the compression tests, we've been able to demonstrate this is sped up by 64 times. But I think what this video demonstrates, so we have a compression test here being performed on one of our printed compression samples. And what we can see here is that there's a very, very nice failure mechanism, if we'd even call it a failure, more compression mechanism of the lattice structure. So the beams don't particularly fail. In fact, on inspection, we find minimal amount of beams that have actually broke at the connecting nodes, but more so they've deformed nicely, uniformly, and the sample has been easily crushed down then. If we compare that with other materials, we mightn't see the same results. Due to the high ductility and this toughness that I talked about with tantalum, this is why we're seeing such a large reduction of our compression sample without a real failure. And again, through our DOEs, we've seen quite a range of compressive strengths that we can achieve here, linked to both the power input or the energy input that we're doing, but also linked to the overall strut size of the beams here on the compression samples. So that covers in terms of solid and porous. We've done quite a good work. We have quite a deep understanding of the capabilities and the behavior of the material. In terms of the powder, which is, again, like I said, a very key piece of this powder bed fusion processes, it's always very, very important. And we've seen good consistency here. We've seen some changes between our virgin powder and used powder, but nothing detrimental. And we've seen quite a stable process as well in terms of the oxygen pickup in particular, which we can see here. Virgin, we've started with 145 parts per million. And this is after used powder. I think this is, forget the number of runs here, but quite a number of runs. We have a very low amount of pickup, so we've only picked up 34 parts per million. Now remember, that's parts per million of oxygen, so very, very stable, which we're quite happy about. And in terms of, again, the PSD, we've not seen major shifts. And in terms of the process and condensates, again, visually, we don't see a large amount of condensate, but again, in the chemistry testing, we don't see large changes here, so that's quite positive for the process. The other part to mention, which Patrick discussed at the end of his section there, is this idea that we've been working with on the combination of materials. So as I mentioned, one of the issues with tantalum, well, there's a cost piece, there's also a weight, which is more the concern. So the weight of the tantalum is 4 times that of titanium. So if we're working with solid tantalum component here, it could be quite heavy. And we feel that it might be more appropriate to use the tantalum specifically where we really need it. And that one area is really the osteoconductive structure, this porous structure. So we have here demonstrated the printing of tantalum onto titanium. So we have a titanium base plate here that we have printed the tantalum onto, and then post-machined this lower section for the various features. Now this is quite nice because with the powder bed fusion process, we can obviously just go from like onto a flat surface. But potentially that could be expanded. But here we've just done like a flat substrate, tantalum printed on top, and it works quite well. We are currently working a little bit more to understand the interface between these two materials and how to improve it. But at the moment, the results are very promising, so it seems like a good option. Now, looking forward, for us, as I said, our goal is really to develop processes and capabilities for our customers. So at the moment, we're seeking customers that would like to collaborate under a contract manufacturing model to utilize this new turnkey material platform we have, i.e. the printing of tantalum. Further investigation around tantalum and titanium. So looking at these interfaces and also leverage the benefits of both materials for this kind of hybrid system. As well as doing biological testing just to validate the sort of biocompatibility studies and various studies that we've seen in the literature, again, to prove that our scaled up industrial system is like for like with the literature. Which I should have mentioned for our mechanical structures and pore structures, we've seen very similar results, so we're quite happy with that. So that's my section finished, and that's the end of the content, but I think we're going to open up now to Q&A, which Patrick is going to lead. So thank you very much.
Yes, please. So Shane and Gordon, you could lead their mics on. Across the ribbon on your Teams portal, boys and girls, there's a question and answers port. Please populate your question in there and we will transfer them to the published section. So with that, there's a number of questions here. I think the first couple, Shane, might be directed at yourself. So the first one, what's the smallest pore and lattice size we have created and tested with tantalum material?
Apologies, what was that? The smallest pore size, is it?
Yes, the smallest pore size.
Smallest pore size. I mean, it depends what someone wants there, really. I mean, we've gone down to around 100 to 200 kind of microns, very, very small. Typically, though, we're actually aiming for a little bit larger than that. In terms of strut diameter, again, it's between 150 to 200 micron would be sort of smaller range that we can achieve. But for us, actually, we haven't focused, I suppose, on going that small on the pore size, actually. So we could probably look at that further. We've actually been focused on a little bit of a larger range. So, and again, above about 200 micron on strut diameter. So been kind of our focus for the moment.
And in building on that, then, what significant challenges did you face in bonding the tantalum and the titanium material within the laser powder bed fusion process?
Significant challenges. Yeah, I think just again, it's around the DOE of the print parameters. So trying to understand what kind of energy do we need to input there to have a strong bond. And also not to have some deformation or some issues or burning of the aluminium or vanadium out of the titanium. So again, just really working with the print parameters. So with this machine, obviously we have full access to change whatever parameters we need. And we've a good understanding from our experience here around how to do those DOEs and how to work with the print parameters. So that's been some of the main challenges.
Okay. And Gordon, perhaps for yourself, have you any experience in relation to 3D or additive manufacturing addressing the imaging rather of MR and CT challenges with tantalum materials?
I guess I don't understand the question. I guess I don't know of any challenges. So,
I think
so I'm not sure I can comment.
Yeah, but what that's potentially alluding to is in relation to its radio opacity. So tantalum has a significant upside of radio opacity within X-rays and also a strong, excellent biocompatibility. So in relation to scanning and X-ray in particular of porous structures that are developed through tantalum material, it's much more vivid, I suppose is the best way of putting it, when compared to some of its alternative materials. So the challenges are pretty minimal, I think, Gordon, is what we're alluding to there.
Yeah,
I don't know of any challenges at this point. So Shane, I mean, you want to comment as well?
Yeah, well, I think actually, I don't remember, Gordon, if you had on your slide there in relation to the scanned images of tantalum. I think you had it here in this slide number 10. So obviously, tantalum is very, sorry, Gordon can speak to this more, but very easy to image. So I guess there isn't really much of a challenge there on that side.
Yeah, I mean, that's the advantage of tantalum and its uses. It's radial opacity. So.
It seems like porous titanium Ti64 has very similar properties to porous tantalum. What makes tantalum more beneficial than titanium?
Yeah, just again, I guess if I go to this slide here, I think that's for us one of the key pieces. So it's this failure mechanism. So if you look in the literature, you might see a little bit around how titanium 6.4 fails. So it hasn't got the same level of ductility as tantalum. And what that really means is that there's a larger amount of plastic deformation, i.e. the material can deform without failing in a plastic mode, which makes it, that's one big benefit. So if, for instance, if there was some large strain on this implant after implantation or during implantation with the tantalum, we're less likely to see a kind of a failure or a breaking off of any of the struts. So that's a big advantage.
Understood.
And again, I would go back to some of the literature information and so forth, specifically on what we had on slide 13. Where we talked about the biological benefits, specifically in applications that a medical implant is going to interface with bone. Of course, osseointegration is one of the big drivers, and there's many studies out there that show that tantalum performs, integrates more efficiently with bone than Ti64, and there's statistical data behind that. Other references indicate, of course, the clotting performance, as well as the extraction of different types of metal ions and so forth. So there's multiple reasons, I think, why you could argue that tantalum would be a more preferred material for the interface between bone and the medical implant.
Okay. There's quite a lot of questions going in here, guys. We'll try and get through them all, right? But the next question, was there specific reasons to the concept laser M2 being chosen dedicated to tantalum? So I'll take that one if that's okay. So from our perspective, our intention here was to develop a process that was capable of being scaled up within a regulated environment that would be similar to those of the orthopedic implant manufacturers of a larger scale. So when we're reviewing the 510K submissions over the past decade or so in relation to 3D printed implants, concept laser M2 was just one of the assets that was chosen across a number of 510K submissions. So from our perspective, we intended to do like for like, not only in a smaller laser powder bed fusion system that would be more suited to a research setting, but something that would be, I suppose, relatable to the development of hip and knee implants in particular. So that was our reason. And on the dedicated aspect of the question, we do tie our materials to our machines, so we do not change our material types within the laser powder bed fusion systems. There's a lot more questions coming in here now.
I think just to add there as well, Patrick, there's quite good control in terms of lots on the system due to the elevator and build platform. So it's very easy for us to completely change lots and then investigate how, say, a different lot of powder or different powder spec is going to affect the process. So easier for us to really clean out the machine, change lots and work that way.
Cool. Next question. How stable is tantalum compared to titanium in terms of mechanical processing, for example, machining milling of a femoral or a tibial tray? So I think this one is specifically speaking to the state of the material within its geometric form. So perhaps I think that question could be alluding to in a powder form, it's more stable than Ti64 in terms of stability, right? Based on our testing criteria completed to date. In its finished state, going through machining trials, it's more different to, I suppose, to a hard metal. Would that be true, Shane?
Yeah, I mean, in terms of the printed, I just in terms of the question, I'm not sure if it's asking if printed versus wrought is similar. So in terms of the printed material, it machines perfectly fine. It's very similar to the way you would machine with wrought. So haven't seen any major differences there. I think, if that answers the question. I don't know if Gordon, if you have anything to add to that.
No, I think that's probably good. I mean, again, on all the mechanical testing, we've done a lot of machining to machine mechanical testing parts, and we haven't seen any issues. It works very similar, if not identical, to wrought tantalum.
Okay. Next question: the different density of tantalum, so 16.6 milligrams per cubic meter versus titanium, I think it's 3.56 milligrams per cubic meter, could limit the applications of orthopedic components entirely printed in tantalum. So the question specifically is, how does it limit the applications when
So I
comparing
guess,
tantalum?
yeah, I guess just this is sort of what we're working on here. So we've also recognized that. So as you said, it's around 4 times more dense than titanium. But looking at the combination of titanium and tantalum, for instance, is quite a good approach. So the porous tantalum really has good benefits and good potential benefits, as we said. So this system here, this TATI hybrid system, the bulk of the structure on the base is titanium, and then the keel and the pore structure is tantalum. So what that means is that kind of density issue is negated, you know.
Mm-hmm.
And that's what we're going to investigate that further as well. So,
okay. Next question: comparing like for like, what is the coefficient of friction of flat plates of tantalum versus titanium alloys against bone, rather than various porous structures?
I guess I couldn't quote any values. I mean, we could take that maybe as something we could look into.
That's a machine flat plate.
Yeah.
I mean, that's a machined flat plate of tantalum versus titanium alloys. Okay.
Yeah.
Okay.
Sorry, I don't have that answer off the top of my head. So
Yeah.
Well, I should mention for everyone on the call that we can send out this slide deck, and any additional questions, please reach out. On the last slide, we have our contact information.
yeah, I'll just pull that up now, actually.
So please feel free to email, and we will send a slide deck in relation to answering any additional questions. So CT and MR challenges make it difficult or impossible to see the fusion progress, in particular in spinal implants. Tantalum light up, in inverted commas, like a Christmas tree. I think that's an answer rather than a question. Yeah, that's true. So the radio opacity of tantalum is it's hard to put a numerical value on it, but it's quite vivid when you see it in an X-ray in comparison to titanium. The only thing I can relate it to is in relation to shoulder implants and the anchorage of glenospheres being installed, and how those anchors that are typically manufactured from titanium or PEEK can kind of fall out after a period of time. But in a tantalum perspective, it's very obvious if the anchor is there or not. So it's one of the main positives within using tantalum material within implants. I think that's one of the final questions. The last question we have in the Q&A, guys, and if anyone wants to put any more, please feel free. The average cost increase for 3D printed tantalum orthopedic components in respect to titanium. So Shane or Gordon, do you want to take that one?
Gordon, if you want to go first.
I mean, the way we look at it is, you know, any additional cost for a tantalum component is extremely small compared to the overall cost profile for the actual surgery for the patient. And then the benefits, I mean, it's a cost benefit question. So there's significant benefit increases, using a tantalum based component. So the actual cost, when it comes to an actual component, I mean, that's going to have to come out in the end, but we don't see it's a major barrier to having tantalum components in the market. Obviously, tantalum is used extensively in medical devices today, as I mentioned earlier. So,
yeah,
okay.
I think I could just add, Gordon, from my perspective, in relation to the downstream value add processing of tantalum material, it far negates that required from commercially pure titanium, and certainly TI64. I think Shane has kind of alluded to the testing that we've completed so far, but there's certain areas that are additional processing that do not need to be added in relation to tantalum and titanium implants that you typically see on TI64 as a whole, at least at this point. Now that would vary obviously from application to application, but yeah, overall, it's certainly looking positive in relation to coming out. Very similar, if not on the south side. So, Shane, anything to add to that?
I think the other thing just to say, I mean, as Gordon alluded to, the powder is actually not a big cost of the process when you look at the overall cost of the process. But the other part is that the powder, due to our partnership here on the collaboration on the powder, we can recycle this more effectively because we have there's full traceability between the two companies, but also our powder is quite stable during processing. So that means we have a higher number of cycles we can run this for printing. So I think there's a number of bits there that kind of start to balance the whole thing out.
Okay. I have no further questions for either of you at this point. So
Great,
with that,
okay.
I'd like to thank you all for joining us. Thank you, Shane, and thank you, Gordon, for your time. Thanks to Ronan as well and Abe on the call in relation to putting this together. As I mentioned, we're more than willing to share all of this information that's been shared on this webinar. Please contact us directly on info@croommedical.com and we'll email you the slide pack. With that said, thank you for your time from all of us here at Croom Medical and Global Advanced Medical. Thanks very much.
Yeah, thank you.
Thanks, everyone. Appreciate it.
Good day.
Yep.
Bye-bye.
Cheers.